welcome to the second talk of this evening. And this will actually be the talk that Stephen also gave at the first meeting of KW Intersections, but I don't think actually many people are here who were at the first meeting. Only
Christopher was there. Yeah.
So therefore, indeed, he is going to give us again this talk. And it's about Hilbert's third problem.
Yes, it is. Yay.
Yay.
We'll sit down because I broke my leg, and because I'm not adequately dedicated to your entertainment. Okay. So Hilbert's third problem. Here is Hilbert. This is a picture of Hilbert. Hilbert was an important mathematician from around 1880 something to 1940 something. He died during the Second World War, although not as a combatant, I believe. He was pretty old by then. He has a great hat, and he's I think rocking this whole look here is pretty rocking actually. Anyway, so he did a lot of important things in algebra and geometry and all over, differential equations too, I think. Very important mathematician of his day. In 1900, he had already achieved considerable reputation, and he came to the International Congress of Mathematicians in Paris to deliver a speech. That speech was about mathematical problems. So this was transcribed and published in German. I think he gave the talk in German. And in it he presented some 23 research problems in mathematics that he thought were of particular importance at that time. They have become very famous. And so here's the talk where he did it. Who of us would not be glad to, blah, okay. So he goes on for quite a while, he's German, about the importance of problems in mathematics and such, and so on. And at some point, he gets to an actual problem. I promise you, he gets to an actual problem. Here. So problem number one is the continual hypothesis, whether there's an infinity, I guess, between the cardinality of the power sets of the integers and the real numbers. I think that's correct. I'm not a set theorist, so I probably mangled that horribly, but it's an important problem in set theory. Solved in the 30s, I think. Anyway, it's kind of cool, but different kinds of infinity. Problem number two is about the consistency, as we would say today, of our axioms of arithmetic, which was, he phrases it here that you should prove that they're consistent, and the eventual conclusion was, not so much, by Gödel and others, and especially in the 30s again. Anyway, we're not going to talk about that. We're going to talk about number three, which is the quality of the volumes of two tetrahedra of equal bases and equal altitude. So imagine a tetrahedron, or I'll draw one for you. A tetrahedron, something like this. It's a pyramid with a triangular base. You might have two which have, let's say, the same altitude, but and equally sized bases, but of slightly different shapes, let's say. So let's say the altitudes are the same and the bases have the same area. Now, in first year calculus, you may derive a rule for the volume of such an object, right? You slice it up in one of these directions, and then you do a similar triangles argument, you integrate, and you get this 1/3, and you get a volume formula for the tetrahedron. Okay? So the point, it's 1/3 times the height times the area of the base. Okay? This is the volume of a tetrahedron. Volume is this. Okay, so the problem here is to prove that if they have equal bases and equal altitudes, then they have equal volumes. So you just say, dude, that's the formula. What's your problem? So it's a little bit deeper than that, luckily. But to explain why, and the big reason is he doesn't want to do that step in there that I said integrate. He doesn't want to do that. He wants to do it with more elementary methods. And understand why and why that's important, or why it's natural to ask that. I'll have to talk about area for a while, because in area things make sense and are great, and volume things are weird, they don't make sense, they're terrible. So in order to explain this problem, which basically says, is it really terrible is volume really terrible? And the answer is yes. We have to understand why we thought that was terrible. So first I will talk about area for a while. This was incidentally the first, I believe the first of Hilbert's problems to be solved. One of his graduate students solved it. A person by the name of Max Dane, who was, as I say, a student of Hilbert at the time. There he is, this young fellow in the back. Not the scary bald guy on the right. I don't know who that is. This is the best Stack Overflow question I've ever seen, by the way. It's, hi, I'm trying to find a copy of this picture, and the answer is, oh yeah, that's just across the hall from me, in front of my office. I'll go take a picture of it. And there it is, Max Dane. Here's a closer look of Max Dane. I think this was maybe a year after. No, I don't remember. I'm not sure. Anyway, this is him. He solved the problem by coming up with something called the Dane invariant, which we will discuss later on. Okay, so first, area, I guess. Let's talk about area. Area of two-dimensional figures. Do you know any area formulas for any particular area shape?
P.
What? Sorry, two people.
AH divided by 2.
Oh, okay, that's
Triangle.
triangle. Yeah, triangle. Excellent, triangle. Okay, more.
R squared.
R squared circle. Yay, circle. We're gonna leave over here because it's a little bit weird. Come back to that. That's it. That's all we know about area.
A2 or AB.
Oh, for the-
rectangle, square.
For squares, yeah, well, of course there are squares. Yeah, and rectangles. But you know rectangles. Any more? You know one. You know one. You don't have to tell me the formula. Just tell me the shape. Shape.
Ellipse.
Ellipse. I'll also go over here with the circle. Pretend that's an ellipse.
B1 plus B2 multiply. B1 plus B2 multiply H
Okay.
divided by 2.
Divided by 2, yeah. So you're both on the trapezoid.
Oh, yeah. Trapezoid.
Yeah, the half average of the top and bottom times the altitude. Good. Anything else? No? Going?
Parallelogram.
Parallelogram. Thank you. He's a plant because he saw the talk before.
That's
I actually have no idea what's coming next. I've completely forgotten your talk.
Excellent. Parallelogram. Okay, so this is enough. Okay, so if you know the rectangle, you can get the square. That's not too hard. If you know the triangle, you get the trapezoid. I'm going to draw the trapezoid back again up here. And you'll cut it in two, and you'll get it from the triangle, let's say. Parallelogram, I'm going to do a couple ways. One, I'm going to actually, you could get it either way. If you know the triangle, you get the parallelogram. If you know the parallelogram, you get the triangle, right? You cut it in half again. Let's say it's two triangles. Rectangle and parallelogram is a special case, or other way, sorry. Rectangle is a special case of parallelogram, so if you knew parallelogram, you can get rectangle. An important one I would like to actually sketch for you is if you know rectangle, you can get parallelogram. This was known by Euclid. There's a lovely argument. I won't give you Euclid's proof because it's not so nice. This is a proof from Simpson, I think. We did an edition of Euclid in like the 15 or 1600s in England. So the argument is if you have two parallelograms which have the same base, let's say this is the base, the common base of these parallelograms. Should I do this a little bit higher so you're not looking through people's heads? No, you're good? Okay. And have the same altitude. So let's say this parallelogram, that one, and let's say this one over here. Okay, so they have the same height and the same base. We're going to prove that they have the same area. Okay, so the lovely proof, the lovely but slightly noisy proof, you take the whole thing, made up the two parallelograms and their common base, and you, on one hand you cut off this triangle, and you end up with that parallelogram. Right? On the other hand, you cut off the other triangle, you end up with the other parallelogram. And the thing is, these two things are equal. And by the parallel sides, it's the same shape of triangle. They don't look like it here because I drew it badly, but the sides are parallel and of equal length. Right? So everything is like side, side, side congruence or something. So these have the same area. So you cross them out and then you get that the parallelograms have the same area also. Okay? Tiny little proof. And so once you know that with the parallelogram, it doesn't matter how you shear it. It always has the same area. Then you can say, once you know the formula for a rectangle, you get the formula for the parallelogram also, because you can take your parallelogram and shear it to be a rectangle, apply your formula for the rectangle, and get the area. Okay. So those are also equivalent. Okay. Actually, yeah, let me stop here for a second to emphasize a couple things. One is that this argument is really cool. Two is that this argument only uses cutting things up into pieces, and finally many pieces, and then putting them back together. And it's very elementary. There's no integration. There's no limits. There's nothing complicated here, right? And the assumptions that we're making about area, if we're developing a theory of area that will support this argument, the assumptions are not that strong. The assumptions are if you have a polygon and you cut it into two polygons, then the area of the two polygons together is equal to the area of the polygon you started with. Right? Cutting things up and moving them around doesn't change their areas. That's all we assume. Very, very minor assumption. Oh. So, but even so, like this, another cool thing I would like to mention, come back, is this argument about shearing parallelograms and keeping their area is crucial to Euclid's proof of the Pythagorean theorem. So you start with these two squares, and you shear that one over and then rotate it into place and then shear it. That keeps the same area the whole time. So the black thing is the same area as this. The red one, you shear it up, and you rotate that 90 degrees. It's a GIF, I can't make it go faster. And then you shear that, and it fills right in. So the common line there is what you get from here, dropping the parallelogram, dropping the perpendicular to there. Right? It's parallel to the sides and through that point. And if you follow where all the points go through this process, you can see that is indeed where both of them end up. This is Euclid's proof, in fact. If you go and read Euclid's Elements, proposition 146, 47, I think. Oh yes, that's right there, 147. This is essentially the proof that he gives. He does it on like papyrus, so it's not animated, but that's the argument. It's lovely. I really like this argument, and it depends crucially on this idea about shearing. Okay, so that's Pythagoras and shearing and area. Okay, so now let's talk about the circle. Pi r squared circle. There is an argument for the area of this thing being pi r squared that looks kind of similar to this, that we just chop things up and move them around. Let me show you that. It's a lovely argument, which I will discredit in a second here. Okay. I'll use this. So we'll take the circle, we'll start by cutting it up into 4 pieces, and we'll rearrange them like this. So we'll take that wedge like so, and then the next wedge like this, and then the next wedge like that, and the next wedge like this. So this is not much use, but you can see this, whatever this is, at least has the same area as the circle. Yeah? Great. So you cut it up some more, into 8, let's say. So let's say 1, 2, 3, 4, 5, 6, 7, 8. And it'll look something like this when you put them back together, yeah? And that has the same area. That's the thing. That was 8. No, we'll do it like this, actually. This is better. Leave that as 4. This one's 8. Let's say we do it 16. It'll look something like this. If you keep doing this more finely, right? What it seems to be moving towards, roughly speaking anyway, is some kind of rectangle. Of what dimension, right? The sides, you cut more finely the sides, and the sides of this kind of squeeze up and become closer and closer to vertical. The bumpiness on the top gets crunched down, right? So this, what is this? This is just the radius, right? The radius of the circle. And across the top, half the circumference went here and half the circumference went there. So it's pi r across the top, pi r across the top, pi r across the top. So this is pi r squared. Okay? Now, this is a lovely and very convincing argument. We noticed right at the end there that there was a step involving limits, right? You do this kind of like infinitely. And there's actually a really subtle and difficult point to fix. This argument is not correct, as stated. There's a significant gap. Yeah, I've talked. What the hell? I'll explain why there's a significant gap. So we assumed here that just because, like, we assumed that every shape along the sequence is pi r across the top and r down the side. And so we assume that the rectangle that we end up with when we pass to the limit is also pi r across the top and r down the side. And when we pass the limit, we think, oh, the arc length will be preserved. Arc length is not continuous under taking limits. So let's let me give you an example under pointwise limits, really. So here we have a equilateral triangle. Let's say it's 1, 1, 1, right? So up and then down, that's 2. Up and then down is 2. Okay? So instead of going up and then down, I'm just going to go up halfway to the midpoint, and then down to the center, and then back up, and then back down. Okay? So it's just like I took the top half here and folded it down. Okay, so it's still, this is still 2. No one disagrees? Okay. Now I'll go up halfway, down, up, down, up, down, up, down. 2. Up, down, 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 up, down. 2.
At the end is 1 equal to.
At the end is 1.
At the end, you have to divide it by 2 because it goes there and comes back. Kind of like off.
Oh, but no, it just starts here and ends there. Like I just, yeah, just go up and then down. Right?
No, but on every, when you go, the two, take one of those.
Like, yeah, one of
Those,
these?
yeah. No, the upside down.
Oh, yeah, like this? Yeah?
Yeah. So when you get closer, the ends tend to, you know,
Collapse.
approach each other and, you know, become one point. They're
Yeah.
infinitely close to each other. So maybe it counts some kind of going there and coming back or something. No,
That's interesting.
No, that's BS. Sorry.
Yeah, the trouble is it's the same shape, right? This little triangle is the same shape as the big triangle. So if it's true, like in the limit somehow, it should be true for the big triangle too. But it's not.
So what's the problem?
Arc length is not continuous under these kinds of limits. So when you pass, like you have a length of a curve, you have a sequence of curves, and the curves tend to another curve, the limit curve. The arc length does not necessarily tend to the arc length. And it can be 2 the whole time and then be 1 in the limit. That can happen. It's not continuous. So when you pass to the limit, your arguments stop and you have to do something else. So, yeah, so it works here, but it doesn't work there, and you need some additional machinery to explain why. It's not very simple. I will just move on. Yeah. So just to mention that, right, so, I mean, this is just cool, so I like to talk about it, but I'll say that limits are more complex than we would like. And
Yeah, but if you, you know, instead of telling at the end it's a rectangle,
right,
you go, I don't know, at the limit of the small triangles
right,
goes, the total of them moves towards 0.
That's
If you
true,
prove
yeah.
that, then it becomes a rectangle. You just get the base bit, you know, the base up and the base down, and you calculate the rectangle. The rest, which is the triangles on top and below,
Go to 0.
they move towards 0, so you get the right answer.
Yeah, so you want to say here, these are like these little pieces of area here,
Yeah.
and these areas go to 0, right?
Yeah. So if you.
Oh yeah, no, these areas go to 0 for sure. Yeah.
And the bottom two. So
So the bottom 2, yeah.
So basically, then you have your proof because you are here.
Oh, no, but
you're not,
I need to know that the length is right. I need to know that the rectangle that I get, the area across the,
okay.
or sorry, the length of the top side is pi r. Because then I'm going to multiply those and get pi r squared. So I really have to know that that rectangle at the end has length pi r.
Yeah, but the rectangle, now we take the bases of the triangles
wanna-
as the basis for the rectangle.
Oh, you just want to count these?
Yeah.
Okay, but how long is that?
So that's pi r.
No,
That-
the
that's-
bumpy
no,
bit,
so
the bumpy
that's-
thing is pi r. It's not exactly pi r, the straight thing. It's something different. I need to know trigonometry. Oh man.
Oh man.
And then I'm probably going to need to prove that like sine x over x tends to 1. I'm going to have some real
But
trouble there.
If we argue that the area of the triangles move to 0,
Right?
then we can argue that the but the area moves towards 0, and because the base is not 0, the height must be 0. So,
Agreed. Yeah. Well, I mean, the base is kind of 0 because they're infinitely small triangles, right? The individual triangles become infinitely small, so they do have base 0 and root 3 over 2 times 0.
but if you calculate the limit of that, then you may reach at the same PR, the total. If I don't have it, I can't have it on top of my mind. But if you write the formula for the base,
Right.
based and then
For these bases.
calculate the limit of that towards infinity,
Oh, okay. Yeah.
you may reach the PR for the total of bases.
Well, you probably do, yeah, but then you'll need to know how to take limits of trigonometric functions, and that's a little bit more sophisticated than just what we thought we were doing, which was just cutting things up and moving them around, right?
Okay.
Yeah, so you're absolutely right. Yeah, if we make this argument more sophisticated, like by using this length instead, right, then we can work around this problem, and then we don't need that it's continuous in the limit. We can just compute the limit, and everything will be okay. No, this is a good idea. Yeah, unfortunately, we would then need to take limits of trigonometric functions, which requires more knowledge. So I really want this argument to work. Right, so because this argument I can show to a 10-year-old, and they'll believe me. They'll be wrong to believe me, because there's that subtle gap, right? But they'll believe me. So, okay, I'll let you figure out how to repair this argument. It's great. Okay, so right, so this is a situation in areas. Okay, we have all these area formulas that we know for polygons. Basically, any kind of polygon that you want. You might know an area formula for a pentagon or something. Well, you can pick a point in the middle and cut it down into triangles, right? You can triangulate your polygons as much as you like, and then you've got triangles, which you reduce to parallelograms, which you reduce to the rectangle. And the rectangle you just assume. That's the definition of area, right? That the area of a rectangle is length times width. Okay, so you do all that. And for polygons, you have a complete story for area, involving only cutting things up and moving them around. Right. And if you want to do curved things, and you say, okay, then I might need to do something fancy. Right? Curving, the transition from straight things to curved things is mysterious or something. There's some complexity there. We have to involve other techniques, like taking limits, either of trigonometric functions, or we solve this problem of the arc length, which can be solved, but takes some work. But still, there's some subtleties there. Okay? So we have in our minds, we have this idea like straight things are simple. Okay? Flat things are simple. They use elementary techniques. Curved things use limits and these other complicated things. Okay, so that's great. We like area. We would like the same thing to be true for volume. It's not. This is still going. Okay. Okay, so if you go into the theory of volume, then we'll do a similar story. We'll get a giant picture of formulas for volume, various formulas for volume. The story with the shearing of a parallelogram, it'll also work for a parallelepiped. You have to do it twice, really, once for the 2 dimensions that you can shear. This is also in Euclid, in his treatment of solid geometry. It's quite lovely. So you again prove that the volume of a parallelepiped is only dependent on the area of its base and the height. And it doesn't matter how you shear the thing. And you think, oh great, now I would like to, get to triangles, because, well, not triangles, but the analog of triangles, which is a tetrahedron. We'd like to say that the volume of a tetrahedron is like half of, or some fraction of, the area of a parallelogram. You can't really do that. If you try to cut up a parallelepiped into congruent tetrahedra, you will have some trouble. Sometimes you can do it, sometimes you can't. I'll show you one example where you can do it, because it's kind of cool. Here it is, dissection of a cube into 6 congruent tetrahedra. I'll make this full screen if I can, so that everybody can admire it. So you start with a cube, and you get a stick, and you put the stick through the long axis of the cube. You admire your work, and then you, okay, you look at this for a second. This is a little fainter than I wanted, but you can see in cross-section, or in projection, the shadow, or the silhouette of this is a hexagon. And it has 6 equally shaped pieces, right? Like kind of like pieces in Trivial Pursuit, or oh no, they have curved things, right? Yeah. So each of these triangular things is itself the silhouette of a tetrahedron. It turns out.
Pyramid. A pyramid?
Yeah, with a
Not
triangular
exactly.
base. Yeah, we'll see. I mean, it's weird because it does funny angles, but you'll, well, we'll see. So we'll cut it up into those 6 pieces in a second here. Taking it off, and then we'll go slice, 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 and then take it apart. So there you have 6 congruent tetrahedra. Isn't that lovely? So for this particular shape of tetrahedron, you can deduce its volume by slicing methods. Right? You have a formula for the volume of the cube, and you know these are all congruent, so they're all equal, and their union is the cube, so it's the volume of the cube divided by 6. Right. Oh yeah, you have to put it back together at the end. That's a rule of magic.
You have to clean up after.
Yeah, the bird has to come back. Isn't that lovely? So, for some tetrahedra, we can do this. Thank you. You too. For other tetrahedra, however, there are. Oh yeah, no, don't show us other people's videos. This is all my videos. For other tetrahedra, there's some trouble doing this. And if you look again in Euclid to see how did Euclid compute what the volume of tetrahedron is, you find out that he did something quite different. So what he does, and I show it here for a regular tetrahedron, but that's incidental. So he deals with the tetrahedron. He cuts it in two, into these 2 funny shapes, which are congruent. So that's fine. And then, well, in this case, they're congruent anyway. And then he cuts off these little widgets from the corners. So now this thing here is a triangular prism, right? And so is that. So these ones we have no trouble with, really. We're willing to say probably that the volume of a triangular prism is going to be the volume of the base times the height. Okay, so that'll be okay. We'll handle that. We'll handle this. The problem is these things are tetrahedra again, and in fact they're tetrahedra of exactly the same shape as the original tetrahedra. So we have just made the problem smaller. Well, we've doubled it and made them individually smaller. So he just continues like this, right? He just cuts those smaller ones into smaller pieces and gets out a little residue, which are smaller tetrahedra, and he takes the limit.
These are not similar to the one we got from the cube.
No, these are not, unfortunately, yeah. These ones are the same shape as the tetrahedron that you started with. So, and you want to be able to do this with any tetrahedron. So yeah. So the ones with that come from the cube are very special, actually. They have a lot. Oh yeah, we're over here. But again, except we'll jump ahead to the parade. It's kind of hard to tell here because Blender does like lensing effects and things. But oh yeah, man, that's hard to tell, isn't it? Okay, so one thing is this angle here is a right angle. Right, it comes from the right angle of the cube. Right, this is half the face of the cube here, and the one on the back there, on that side, is also right angled. There's a 45, 45, 90 triangle. It's half of the face. Yeah, and the same thing with, of course, all the other ones because they're congruent. And actually, I think this angle here is also on the face. This face is also 90 degrees. Oddly enough, or maybe it's this one. Yeah, I'm not sure. So yeah, they're very special. They're called Schleifli orthoschemes. It's kind of a cool band name, I guess. But Schleifli and the orthoschemes. Yeah. So unfortunately, they're a very specific shape, and this method is supposed to work for any kind of tetrahedron at all. And it only works by reducing to smaller copies of the same tetrahedron and then continuing to do that and taking the limit. So Gauss apparently once complained in a letter to someone, I forget, it's mentioned in this thing by Hilbert, his talk by Hilbert. He said, "This sucks," I'm paraphrasing, "this sucks, why do we have to use limits in the theory of volume for polyhedra? And we should expect, and by analogy with the situation for area, that flat things with straight edges are simple, and we can do those. We can do a theory of volume just by cutting things up and moving them around. Curved things, we use limits. That's no problem. The sphere, sure, to get the volume of the sphere, we'll accept taking limits. But for this is ridiculous. This is offensive. Why do we have to do this?" Okay, so this is the question that Hilbert actually asked. No, this is not Hilbert. Where is Hilbert? Hilbert is
The one before
this
that.
one. Yeah, Hilbert. Sorry, Hilbert himself, with his awesome hat, is there. With this, here's the paper. Yeah. So he discusses this girdling, as Gauss wrote to. So he discusses this problem and says, "Nevertheless, it seems to me probable that it can't be done." and that in order to do a theory for volume of a polyhedra, you have to use some limiting process or something like this. That merely cutting things up into pieces and moving them around is not enough. This is what Hilbert proposed. He said, I don't think it's enough to just cut things up into pieces and move them around. Prove it. And his student did that. The proof is very interesting. First idea of it is to say, is to introduce a new invariant. So if you have two polyhedra, let's say or two tetrahedron that you have, and you want to say, I want to prove that this one cannot be cut up into pieces and reassembled to make that one. How would you prove that? Well, one way you do it is if they have different volume to begin with. Right? And you say, of course I can't do that because my steps of cutting things up and rearranging them, they preserve the volume. In other words, the volume is invariant under my operations. So if I don't start and end with the same volume at least, I can't possibly do it. What Dane did is introduce a new invariant, not the volume, but another thing, not even a quantity, and I won't explain exactly what it is. It lives in a vector space, but it's technical, and we'll skip it. I'll just ask you to trust me on certain points here. The Dane invariant for a polyhedron works like this. I take you go through all the edges of the polyhedron. Sum over edge. Let's say sum over edges of your polyhedron. And you take two things. For each edge, you take the length of the edge, which is a number. And the other thing you take is the angle between the faces that meet at that edge. Let's say angle, let's say of the edge. And you multiply. For those in the know, I'll say this is it's a tensor product of vector spaces. These things live in vector spaces over the rational numbers. You'll see why it has to be just over the rational numbers in a second, but yeah, so then this is tensor product, and the whole thing lives in another vector space over the rational numbers. For those who are not in the know, let me just say this is a weird way of taking products that is very generic, and it behaves like a product. That is really what matters for us. It behaves like multiplication, and we'll see a couple examples of that where, like we have the distributive law and things like that, that things just work nicely the way that you would expect.
Is it the same as multiplying a horizontal vector and vertical vector? And one row and one column in a matrix?
Yeah, but, not exactly, no. Part of the problem is that these vectors aren't infinite dimensional.
Oh no, but this is one dimensional. This is just a series of numbers. This size.
You would think so. Yeah, so length, right? It's just one number, right? Yeah, but because it's a vector space over the rational numbers, numbers which are rationally independent are treated as being in different directions. Okay, so like 1 and pi, for example, or 1 and square root of 2 even. Right? These are different directions in the vector space. So you can't multiply the vector 1 by anything to get square root of 2.
Yeah, but we are talking about length and angle. So these are, although different units, different types of quantity. That's why one is a row, one is a column. Okay. But you can get a number by multiplying these two, get a single number. Is that?
Well, you can, but it's not this. Yeah, but it's not this multiplication. No, this is an abstract multiplication which it generates vectors, in fact. But
so the output, the result of the multiplication is another vector, not a number.
Yeah.
Okay.
But it's a vector again in these funny dimensional weird vector space. Yeah, over rational numbers as the scalars, not real numbers as the scalars. So yeah, I mean this was already an infinite dimensional vector. This is already an infinite dimensional vector, and then we get a new infinite dimensional vector by tensoring them. Yeah. Yeah. This makes sense.
Yeah, no,
okay.
It just gives you another vector or whatever space it is.
Yeah. A vector from some strange space. All right, so we go over all the edges of your polyhedron, and you multiply the lengths and angles at each one, and you add them up. Okay, and you get some vector in some weird space. So the claim is, first of all, that this is an invariant. If you cut the thing up and split off, that it will not change. This sum will not change. And then the second part is that this vector, this invariant turns out to be different for different tetrahedra. Yeah? That part I will maybe skip because I don't remember how it goes right now. But I'll show you though roughly how this turns out to be an invariant. So let's say that we have a polyhedron and we cut it into two pieces, and then we're adding up the things like this. So there's a couple things that might happen when we cut. One thing that might happen is we cut along an edge. Okay. So before maybe we had some edge, let's say like this or something. Here's this edge. How does it make like this? For example, something like this, and we cut along this edge, and then we end up with something like some thinner slice here, right, and some other thing over there, which something like this. Yeah, we cut along the edge. So in this one, let's look at the contribution only of this edge that we cut along. Okay, this contribution of this. This is some length, tensor, some angle. Theta, let's call it, whatever. Okay. Over here, let's look at, we have two edges corresponding to that one. One of them is, they're both length. And then there's some different angles between the two faces here, but they add up to whatever these two angles are. Let's say they're, say this one is alpha, this one will be theta minus alpha. Because we cut through the edge, so it just cuts the angle into two pieces. So this one over here we have alpha, and then theta minus alpha. Now, because this thing acts like a product, we can factor out the L. And we get alpha, theta minus alpha, and then the alphas cancel. Everything's fine. And we got the same number. Well, vector. Same thing. Right? So this is one situation. We might cut along an edge. Or let me say this a different way. Edges that we count while we're computing the invariant for after the fact of cutting will include edges that arise in this way, perhaps. And they also include edges that arise in this way. So let's take the same thing, I guess. Something like this again. Let's say we cut, the main problem is what I want to draw over here. Let's cut, I don't know, we'll cut through here or something. Yeah, up here. Yeah, something like that, okay? And we'll pull it into two pieces. So one of them is smaller like this. And one of them is bigger like this. A piece at the back. Okay? So over here, in fact, this was not an edge. Okay, so this was 0. We didn't count anything there when we were doing the invariant for that one. Over here, we've got some edges. I'm just going to consider these two edges here. It's a similar story for the two on the other side, if they exist. So they have some length. It's the same length for the two of them. So it's length. I was reading this in red. Length. And the other one is length. And they have, again, some angle between these two faces and some angle between these two faces. Those two angles add up to 180 degrees now, or pi radians, as I'll say, because it used to be a straight thing, right? So this is, let's say, alpha plus pi minus alpha. Good. And so again, we say, we'll factor out the L, we'll cancel the alphas, and I'll say, that's not 0 necessarily. That's pi. Okay, wow. So we'll introduce one more thing, which is that pi is 0. Well, we'll work modulo pi.
Even in the previous case, we are creating some edges that were not there.
Yeah, there were these two edges. Oh, you were looking at these edges
the
down here?
middle ones, yeah.
Yeah, so one cut may actually produce many of these cases. So it's really more, what I should say is I'm not looking at what a cut can do, the different things that a cut can do, but say the different kind of origins of an edge in the after the fact picture. So here, I'd say if we add this edge and this edge to our sum, where did those edges come from? And in this case, those two edges came from splitting up that edge, cutting through it. Whereas these edges down here and here, I would say they came from cutting a face, so they would be under this case.
Oh, okay.
And then
whenever we cut, we get at least 2 extra edges when we cut it that way. So it's
Sure.
always 2 pi, which is actually 0 in trigonometry.
Oh,
Because
from
2 pi
on
is
the other side.
It's always 0 anyway.
Oh, on the other side, yeah, because there's going to be a 2 pi there.
And 2 pi is always 0. It's
I don't know, because I'm going to I cut through the bottom face this time, right? I cut through the bottom of this thing when I cut through here. But on the opposite thing, I didn't hit a face, I hit an edge. So I don't
yeah,
get,
but
I
still
don't get
you
2
get
pies.
you separate, you get 2 different edges. So you get an extra edge, yeah, you get 3 pies.
Yeah, so the 3 pies is not 0.
Yeah.
Aha. But pi, no, it is because pi is 0. We're just going to declare that, which means we'll work modulo pi. Okay. After the fact, we just decide that's what we're going to do. What else can happen? There's one more thing that can happen, and now I don't remember what it is. Oh yeah, sorry, this is 0. So this is, pi is 0, so this is L tensor 0, and one of the ways this product works, like other products, is that 0 times anything is 0, so this works. This is a 0 vector, and that's a 0 vector. Anyway. Oh dear, what's the other way that we can make edges out of this? I thought there were 3. I haven't given this talk in 2 years.
Through one of the
Cutting through a
corner and through the other edges.
That's
Not along
okay.
not along the edge, but through the corner.
That should be okay, because on the direction that I'm going through an edge, I'll just do that treatment, and on the other side where I'm going through a face, I'll just do this.
Yeah.
I think that's okay.
So basically.
Oh yeah, sorry, I cut an edge in 2. So I'll cut this way, let's say. And so we're going to look at this edge here. Yeah, this is actually the easiest case. I should have done this first. Maybe if I'd remembered it. So then we cut into 2 pieces, and again we look at just the contribution of the edge of this edge that we wish to consider. Okay, so then this is over here is like L tensor theta. I don't know, some length, some angle. I don't know. Here is the same angle for both of them, and the lengths add up correctly. Yeah. So again, I factor out things. This is the same as what I started with. This is the length added. And there's a distributive law with this product that I have not really explained. So no matter what you do with the cutting things up or putting them together, which is just the right to left of this sum will not change, and so it is invariant for all tetrahedra. But you can compute, for example, I think with the one for the cube, you actually compute that with all those right angles in it, that tetrahedron, you compute that this thing is 0, again, because there's so many pi over 2's, basically. And the pi over 2's add up to make pi, and the pi is 0. So you end up with 0. But if you do it for the regular tetrahedron, for example, it's some other value. And you say, oh, so you can't cut up the regular tetrahedron and make one of those funny tetrahedra, even if it has the same volume, because they have the wrong Dane invariant, which is this funny quantity. Hilbert was right.
So all we need to do is find some two shapes with the same volume and different invariants.
Yep. And then you're done. Yep. And you say, your slicing doesn't work. Yes?
Does the converse hold, where if you have 2 things with the same volume and Dane invariant, you can make them, they are scissor congruent?
I have been told that this is true. I have not read a proof of it. But yeah, I've been told that the 2 together make a complete system of invariants. And I think that's true also in 4 dimensions. But in 5, I think you might need something else. This is all from memory from some time ago, so don't quote me. But yeah. Yeah.
What does this system think about moving like a corner or something?
Oh, just like stretching it out?
Yeah, yeah.
Yeah, so if you, let's say if you shear, for example, a nice one, like you take a tetrahedron and you just move the top point, right, and shear it. So it'll keep the same volume, but the Dane invariant will change dramatically. In fact, it's totally discontinuous in such a movement, it turns out. Yeah.
So is this still a good proof to say like they don't have the same volume?
No, they have the same volume, but they don't have the same this thing, whatever the hell this thing is. Yeah. So it could be like, yeah, I don't know. Your cubes have the same volume, but they're not the same color or something. So and they change color when you shear them. So, yeah.
Or when you shear them, you can't then cut them up and stick them
And
back together.
put them back together, yeah.
Back in that original shape.
Yeah, because of the Dane invariant, because the color was
Compress them
just
into
changed.
shape.
You change the color, and that's it. Right? Except the color is a vector, so it's kind of, well, color is kind of a vector, but not this kind. It's weird.
Going back to two-dimensional figures in areas, are there good proofs? Are there any proofs for irregular polygons or convex polygons?
Yeah, you can always triangulate a polygon, whether convex or not, or yeah, as long as it's a polygon, we can reduce it to triangles, basically, and then everything is okay.
Are there theoretical proofs for such polygons?
Sorry, are there what proofs?
Are there theoretical proofs? Can you theoretically prove that cutting and slicing will?
Oh, I see. I don't know.
Because there was this image where you sliced a pentagon into 5 triangles.
Oh, yeah.
I don't know to say if it's not regular, if it's a weirdly shaped pentagon.
Right.
I don't know to say in argument if congruent triangles will work. I don't know how you
Oh, yeah, the individual triangles may not be congruent.
I don't know how you would go about slicing it. Like, how would you?
Oh, okay. Yeah, like say you want to turn it into a square, which has the same area. How should you slice it up? Oh, okay, yeah. Yeah, I do know a procedure for this. You can unpack all of this into a procedure at the steps that we did with pentagons and whatnot. You can, so one very crude way to proceed is you take all of the vertices, let's say, and you just cut parallel lines through all of them. And then if you have rotated it so that none of those go through 2 vertices, then what do you have? You should have trapezoids everywhere, yeah? At worst? Yeah, trapezoids are triangles, and then the trapezoids you can cut in 2, and then you'll triangulate it. Once you've triangulated, right, then you can take each of these triangles and you can turn it into a parallelogram by introducing its, well, you can double up the whole figure and introduce a parallelogram. Then you can do that parallelogram argument to turn that into a rectangle.
Yeah.
Okay, so you'll slice all this up again and rearrange it again to get them rectangles, and then you'll have a bunch of rectangles. And then, okay, then yeah, there is a way to change a rectangle into a square, for example, or you can, or to change a rectangle into another rectangle of any specified width that you want. So then you could turn all of these rectangles into rectangles of the same width, and then stack them up and get one big rectangle, and then say, I know the volume, I know the area now. So yeah, there are such procedures. This one obviously is not going to be the most efficient, unless you, yeah, I don't imagine it's going to be the most efficient. And I vaguely recall seeing something about work on making better methods for actually doing the decomposition, but I don't know anything about it really.
It is just getting convinced that there are.
Yeah, I'm not sure what I said here was right.
Yes,
Sounds right. Oh, yeah.
So earlier on, you showed a method that you cut it, you got 2 triangular prisms and 2 smaller identical tetrahedrons.
Yeah, similar to the original. Yeah, yep. This one. Yep.
Yeah, because why couldn't you just then say, all right, the 2 smaller identical tetrahedrons, you know their side length relative to the bigger one, so then you just rearrange the equation so they're on the other side, and so then the bigger tetrahedron minus those 2 is equal to the volume of the.
Yeah, I really like this question. The problem is that you would like to prove the similarity results starting from this theory of area. Yeah, so an implicit assumption there is if I scale the whole tetrahedron down to by a constant factor, right, that the resulting tetrahedron's volume is, that factor to the 3 times the volume of the whole thing. This needs proof. And this, at the kind of foundational level that we're working at, we don't have that theorem yet. And we would prove it, in fact, afterwards. By having, essentially, we would prove it to be true for parallelograms, or we would maybe assert it's true for rectangles. and then derive it using all of these methods to get all the other things, parallel pipets, rectangular solids, and then derive it from all these methods for all other solids. But we can't get to all other solids using these methods, so we're kind of screwed. Yeah. So if we have that axiom, then we're great. Yeah.
What's the exception that then found for this? Because it still doesn't prove that we can't do it. That means the answer to the third problem is no.
Oh yeah, no,
He proved it, but there's something that contradicts, and there's some two shapes with equal volume with different invariants. So what's the example?
I don't remember what Dane gave. You can do it with like a regular tetrahedron in a cube or something. For a cube, it'll be 0, and for the regular tetrahedron, it's something else.
Oh, okay.
Yeah.
So, a cube is always 0, right?
Yeah, because it'll be like length times pi over 2, but then how many? 12 edges. 12 of those. You move the 12 in.
Find a tetrahedron with the same irregular tetrahedron with the same.
Yeah, regular or irregular,
with
whatever
the
you
same
want.
volume.
Yeah. Yeah, I don't know exactly the example he gave, but something like that would work.
So it's not that difficult an example. Just
Yeah, no. Yeah, the hard part is coming up with this ridiculous thing.
Yeah.
Yeah. Yeah. The mysterious mind of Max Dane, a young man around 1901.
Got an A+, I guess.
Yeah, he got his PhD, that's for sure. Yeah. Okay, it's about an hour. Why don't we cut it short? And we can mingle if you like. Mark is here now, so we can mingle with Mark. Cool.
Thank you.